Hello everyone, we start our course of formal languages, Automata and codes, and our next lecture will be lecture number 15. And this lecture is devoted to defining non-regular languages. Regular languages can be infinite, at most as our example have demonstrated. The fact that regular languages are associated with automata that have finite memory, however, imposes some limits on the structure of a regular language. Some narrow restriction must be obeyed if regularity is to hold. Intuition tells us that a language is regular if only if in the proceeding any string the information that has to be remembered at any stage is strictly limited. This is true, but has to be shown precisely to be used in any meaningful way. There are several ways in which this can be done. Using the pigeonhole principle. The term pigeonhole principle is used by mathematicians to refer to the following simple observation. If we put an object into m boxes, pigeonholes, and if n is greater than m, then at least one box must have more than one item in it. This is such an obvious fact that it is surprising how many deeps results can be obtained from it. Example, in the language L, which consists of such words a in power n, n in power n, where n is greater or equal 0, is regular. The answer is no, as we show using a proof by contradiction. Suppose L is a regular language, then some deterministic finite acceptor M with the set of stage Q, our alphabet A and B iteration functions delta and initial state Q0 and the set of final states F exist for it. Now look at the image of delta star of Q0 A in power I for any I from the set of positive integers. Since there are a limited number of i's, but only a finite number of states in the automaton M, the pigeonhole principle tells us that there must be some state, say Q, such that delta star of Q0 A in power R n is equal Q, and delta star of Q0 A in power M is equal Q, with n is not equal M. But since automaton M accept the word A in power n, B in power n, we must have delta star of Q B in power n is equal to Q F, which is belong to the set of final states F. From this, we can conclude that delta star of Q0 A in power M, B in power n is equal to delta star of Q0 AM Bn is equal delta star Q B in power n is equal QF, which is belong to the set of final states F capital. This contradicts the original assumption that the automaton M accept word A in power n, B in power n only if n is equal m. and leads us to conclude that the language L cannot be regular. In this argument, the pigeonhole principle is just a way of starting rigorously. What we mean when we say that a finite automaton has a limited memory. To accept all a in power n, b in power n, an automaton will have two different type between all prefixes a in power n and a in power m. But since there are only a finite member of internal state with which to do this, there are some positive integers n and m for which the distinction cannot be made. In order to use this type of argument is a variety of situation. It is convenient to codify it as a general theorem. There are several ways to do this. The one we give here perhaps the most famous one. Here is what we know about transition graphs for regular languages. If the transition graph has no cycles, the language is finite and therefore regular. If the transition graph has a cycle with a non-empty label, the language is infinite. Conversely, every infinite regular language has a deterministic finite acceptor with such a cycle. If there is a cycle, this cycle can either be skipped or repeated in an arbitrary number of times. So if the cycle has a label v, and if the string w1, v, w2 is in the language, there must be strings w1, w2, w1, vv, w2, w1, vv, w2, and so on. We do not know where the deterministic finite acceptor this cycle is, but the deterministic finite acceptor has n status. The cycle must be entered by the time m symbol have been read. If for some language L capital there is even one string w that does not have this property, the language L cannot be regular. This observation can be formally stated as a theorem called a pumping, the pumping lemma. The pumping lemma. The following result now are the pumpkin lemma for regular languages. Uses a pinhole principle in other form. The proof is based on the observation that in a transition graph with n vertices, any walk of length n or longer must repeat some vertex. That is, contain a cycle. Theorem. Let n be an infinite regular language, then there exists some positive integer m such that any word w from the language L with length greater or equal m can be decomposed as w is equal x, y, z with where the length of the word x, y is less or equal m, and the less of word v is greater or equal 1, so that WI is equal x, y in power I, z. Is also in the language L for all non-negative integers I. To perverse this, every sufficiently long string in the language L capital can be broken into 3 parts in such a way that an arbitrary number of repetition of the middle part yields another string in L. We say that the middle string is pumped. Hence, the term pumping lemma for this result. The proof. Let L is regular, if L is regular, then there exists a deterministic finite automata that recognizes this language L. Yeah, let's add a deterministic finite automaton has states labeled Q0, Q1, Q2, so on, Qn. Now take a string W in the language L so that the length of this word W is equal or greater M, which is equal N plus 1. Since the language L capital is assumed to be infinite, this can always be down. Consider the set of states the automaton goes through as a process W, says Q0, Qi, Qj, so on, Qf. Since this sequence has exactly the length of W plus 1 entries, at least one state must be repeated. And such a repetition must start no later than the nth move. Thus, the sequence must look like Q0, Qi, Qj, so on, Qr, so on, Qr, so on, Qf. Indicating there must be sub-words x, y, and z of the word w, such that delta star of q0x is equal qr, delta star of qry is equal qr, delta star of qrz is equal qf, with the following properties: that the length of the word xy is less or equal n plus 1, which is equal m, and the length of the word y is greater or equal 1. From this, it is immediately follows that delta star of q0 xz is equal qf, as well as delta star of q0 x y square z is equal qf, and delta star of qr x y in power 3 z is equal qf, and so on, completing the proof of the theorem. We have given the pumping lemma only for infinite languages. Finite languages, also always regular, cannot be pumped because pumping automatically creates an infinite set. The theorem does not hold for finite languages, but it is vacuous. The M in the pumping lemma is to be taken larger than the longest string, so that no string can be pumped. The pumping lemma, like to pigeonhole argument in example 406, is used to show that certain languages are not regular. The demonstration is always by contradiction. There is nothing in the pumping lemma. As we have stated, it's here, that can be used for proving that a language is regular. Even if we could show, and this is normally quite difficult, that any pumped string must be in original language, there is nothing in the statement of theorem 4.8 that allows to conclude from this that the language is regular. Example: use the pumping lemma to show that the following language, which considers a word of the form a in power n, b in power n, where n is any non-negative integer is not irregular. Assume that the language L is irregular, so that the pumping lemma must hold. We do not know the value of m, but whatever it is can always choose n equal m. Therefore, the substring y must consist entirely of the symbol a's. Yeah. Suppose the length of the word y is equal k. Then the string obtained by using y is equal 0 in equation 1. Yeah. The equation is w I is equal x y in power I z is y w 0 is equal a in power m minus k b in power m. And clearly this word is not in the language L. This contradicts the pumping lemma and thereby indicate that the assumptions that the language L is regular must be false. In the applying the pumping lemma, we must keep in mind that the theorem says we are granted the existence of an integer m as well as the decomposition x, y, z, but we do not know what they are. We cannot claim that we have reached a contradiction just because in the pumping lemma is violated for some specific value of integer m or the word x, y, z. On the other hand, the pumping lemma holds for every word w from the language L and every positive integer I. Therefore, if the pumping lemma is violated even for one w or I, then the language cannot be regular. The correct argument can be visualized as a game we play against an opponent. Our goal is to win the game by establishing a contradiction of the pumping lemma, while the opponent tries to foil us. There are 4 moves in the game. The first, the opponent pick m. Given m, we pick a string w in the language L of the length equal or greater than m. We are free to choose any word w subject to w belongs to L, and the length of the word w is greater or equal m. The opponent chooses the decomposition x, y, z. Subject to the length of the word xy is less or equal m, and the length of the word y is greater or equal 1. We have to assume that the opponent makes the choice that will make it hardest for us to win the game. We try to pick I in such a way that the pump and string wi. Defined is in equation 1, yeah, which is w I is equal x, y in power I, z is not in language L. If we can do so, we win the game. The strategy that allows to win where the opponent's choice is tantamount to prove that the language is not regular. In this, step 2 is crucial. While we cannot force the opponent to pick a particular decomposition of the word W, we may be able to choose the word W so that the opponent is very restricted in the step 3. Forcing a choice of the word X, Y, and Z that allows us to produce evaluation of the pumping lemma in our next move. Example, shows that the following language is not regular, which consists of the word the concatenation of any word of alphabet sigma, W, and reverse word of W. Whether M is open and peak in step 1, we can always choose a word W as shown in the following figure. Because of this choice and the requirement that the length of the word x, y is less or equal to m, the opponent is restricted in step 3 to choosing a string y that consists entirely of the symbol a's. In step 4, we use I is equal to 0. The string obtained in this fashion has a few symbols a's in the left when the right, and so cannot be of the form V, W, and W reverse. Therefore, the language L is not regular. We note that if we have chosen a string W is too short, then the opponent could have chosen a string Y with an even number of the symbol B's. In this case, we could not have reached a violation of the pumping lemma on the last step. We would also fail if we want to choose a string consisting of all symbol A, say, equal as the word W is equal A in power 2m, which is in the language L. To define it, the opponent need only pick y is equal AA. Now, as the word WI is in the language L for all I, and we lose. To apply the pumping lemma, we cannot assume that the opponent will make a wrong move. If in the case where we pick W is equal to A in power 2m, the opponent were to pick Y is equal A. Then the word W0 is a string of the odd length and therefore is not in the language L. But any argument that assumes that the opponent is so accommodation is automatically incorrect. The next example. Let alphabet sigma consist of two symbol A and B. The language L, which consists the word from the which is generated by alphabet sigma of the following form that occurrence of the symbol A is less in the word, this word is less with the occurrence of the symbol B on the word is not regular. Suppose we are given M. Since we have complete freedom in choosing the word W, we pick W is equal to A in power M, B in power M plus 1. Now, because the length of the word XY cannot be greater than M, the opponent cannot do anything but pick a string Y with all symbols A's. That is Y is equal to A in power K, where K is greater 1 or equal 1 and less or equal M. We now pump up using is equal to the resulting string W is equal A in power M plus K, B in power M plus 1 is not in the language L. Therefore, the pumping lemma is violated, and hence the language L is not regular. The next example. Let alphabet sigma capital consists of two symbols A and B. The language L, which consists of all words of the following form A, B in power N, A in power K, where N is greater K and K is greater 0, is not regular. Given M, we pick as our string. W is equal to A, B in power M plus 1, A in power M, which is in the language L capital. Since the constraint, the length of the word xy is less or equal m, both a and y must be in the part of the string made up to apes. The choice of the word x does not affect the argument. So let us see what can be done with the word y. If our opponent pick y is equal a, we choose I is equal 0 and get a string not in the language of the form, yeah, a b star a star. If the opponent picks y is equal a b, then we can choose I is equal 0 again. Now we get the string a b in power m a in power m, which is not in the language L. In the same way, we can deal with any possible choice by the opponent, by proving our claim. Next example. Let alphabet sigma consists of two symbols A and B. The language L, it consists with the words A in power M, where N is a perfect square, is not regular. Given the opponent's choice of M, we pick W is equal A in power M square. If the word W is equal X, Y, Z is the composition, then clearly Y is equal A in power K, with K greater or equal 1 and less or equal M. In that case, W0 is equal A in power M square minus K, but M square minus K is greater M minus 1 in power 2. So that the word W0 cannot be in the language L. Therefore, the language is not regular. In some cases, closure properties can be used to relate a given problem to one we have already classified it. This may be simply a direct application of the pumping lemma. Next example. Let the alphabet sigma consist of two symbols A and B. The language L, which consists of the word of the form. So it's here is a misprint. Sigma must be consist of three symbols A, B, and C. Yeah, and language consists of the symbol A, N, B, K, C, and power N plus K, where N and K are non-negative integer, is not regular. It is not difficult to apply the pumping lemma directly, but it is even easier to use closure under homomorphism. Take H of A is equal A, H of B is equal A, H of C is equal C. Then H of L is equal, consists of the word of the form A in power M plus K and C N plus K, where N plus K is greater or equal 0. And hence, this image consists of the word of the form I in A in power I and C in power I, where I is a non-negative integer. But we know this language is not regular. Therefore, the language L cannot be regular either. Next example. Let the alphabet sigma consists of two symbols A and B. The language L, it consists of the whole N and power N, B and power L, where N is not equal L is not regular. Here we need a bit of ingenuity to apply the pumping lemma directly. Choosing a string with N is equal L plus 1 or N is equal L plus 2 will not do, because our opponent can be always choose a decomposition that will make it impossible to pump the string out of the language. That is, pump it so that it has equal numbers of A's and B's. We must be more inventive. Let us take N is equal m factorial and L is equal n plus 1 factorial, if the opponent now chosen a string y by necessity consists of all a's, of the length k less m, we pump I times to generate a string with m factorial plus I minus 1 k a's. We can get a contradiction of the pumping lemma if we can pick I such that m factorial plus I minus 1k is equal to m plus 1 factorial. This is always possible because I is equal 1 plus m multiply m factorial divided by k, and k is less or equal m. The right side is therefore is an integer, and we have succeeded in violating the condition of the pumping lemma. However, there is a much more elegant way of solving this problem. Suppose the language L were regular, then by theorem 4.1, the language L is and the language L1, which is equal the complementation of L intersection with L of A star B star will be also be regular. But L1 is equal L1 consists of the word of the following form A in power n, B in power n, where n is greater or equal 0, which we have already classified it as non-regular. Consequently, the language L cannot be regular. The pumping lemma is difficult to understand, and it is easy to stray when applying it. Here are some common pitfalls. Watch out for them. One mistake is to try using the pumping lemma to show that language is regular. Even if you can show that no string in the language L capital can ever be pumped out, you cannot conclude that L is regular. The pumping lemma can only be used to prove that a language is not regular. Another mistake is to start, usually inadvertently, with the string not in the language L. For example, suppose we try to show that L, the language L, consists of A in power n, where m is a prime numbers, is not regular. An argument that starts with given m, let w is equal a in power m, so on, is incorrect because m is not necessarily prime. To avoid this pitfall, we need to start with something like given m, let w is equal to a in power m, where m is a prime number larger than m. Finally, perhaps at most common mistake is to make some assumption about the decomposition x, y, z. The only thing we can say about decomposition in what of the pumpkin lemma tell us, namely that the word y is not empty and that the length of the word xy is less or equal m. That is, the word y must be within m symbols of the left and n on the string. Another also make an argument invalid. A typical mistake in trying to prove the language in equation 2, is not regular, is to say that y is equal a in capital K with K odd. Then, of course, w is equal x, z is an even length string and thus not in the language L. But the assumption on K is not permitted and the proof is wrong. But even if you master the technical difficulties of the pumping lemma, it may still be hard to see exactly how to use it. The pumping lemma is like a game with complicated rules. Knowledge of the rules is essential, but alone is not enough to play a good game. You also need a good strategy to win. If you can apply the pumping lemma correctly to some of the more difficult cases in this course or lectures, you are to be congratulated. So I finish my lecture. Thank you for your attention. Thank you for everything. I wish you good luck, good health, and goodbye.